Again, good morning and welcome to Astronomy 100. Today we're starting actually week 5, and this is basically a plan for how the week is going to go. We have an exam that is coming soon, so we really have to start getting ready for it. And I will be talking about that. Before I do that, we have today quite a few things to talk about. So one of the things is the 2 units that are introduced this week. And the 2 units, of course, have to do with the solar system. The first one about its structure, and the second one is basically, and also how it came to be, and how do we know what we know? I mean, how do we know its history? How do we know its structure, and so on and so forth? Obviously, this is really not the details that probably we're going to go down the road on them because we're going to delve far more. I'm going to take you on a tour of the solar system. As a matter of fact, we're going to have a simulation using my other computer, my laptop actually, that has a nice view of the solar system. We're going to explore all of the planets of the solar system, including some of the outer objects. And we're going to talk about how the solar system formed. We're going to talk about the age of the solar system and how we know these things, and basically how we determine these things. As we said a long time ago, this is not in lieu of reading the units. So you're really still required to read those units. There is a homework assignment this week. So I'm going to go through, I think, like what, 5 problems 10 through 14 from page 99 from the book. And either edition, it's the same page. So if you have the 5th edition or the 10th edition, it's the same thing. Somebody sent me a message about the 4th edition. I really don't know much about the 4th edition, as honestly. But just in case, I also included the problems on Canvas. So I copied them, basically. I wrote them manually. And so that you guys can see them too there, just in case if you still did not receive your book or something like that. So this is basically what's happening this week. What happened last week was the quiz, the biggest deal. So what I did today is actually I went through the quiz, went through your attempts and regraded them. That's why I did not really give for each question like 1 point. I gave it more than 1 point, depending. And depending on how close your answer is, sometimes you probably have estimates, and you can see clearly there, and sometimes it asks you to write numbers, but you put it in words. That's why I give you credit, for partial credit, sometimes even full credit. Some of those questions that have like matching things, as far as Canvas is concerned, it's an all or nothing, meaning you could get like 5 out of 6 correct, and you still end up with a 0 points. So what I do in this case, I override the grade, whatever Canvases give you, and give you the credit for what you're supposed to have for those questions. So I regraded everything. And sometimes when there is multiple attempts, and I'm kind of saddened actually to see that some of you did not take all of the attempts that you're deserving. I mean, you're entitled to, because you have 3 attempts at it, and some of you did only 1 attempt. I wish you did more. You give yourself more choices, because the system, Canvas, takes the highest score. So you're not going to lose anything. Even if you get the perfect score and you take it again and you don't do as well, you still are going to get that grade. The point being in here is some of you guys did not take full advantage of these 3 attempts, and that's really not good. I wish that you did at least more than 1 attempt. In the case when there are multiple attempts and the grades there is a big disparity between 1 attempt and the next, I usually look only at the highest grade and then regrade that one. Now, here is the problem. Since there are too many classes and I really have to go through all of them, this is the plan I have attempted. Now, if you look at your work and you see you might deserve a higher grade than even what Canvas has given you or what I regraded, based on another attempt, please let me know so that we go through it in detail and see if that's true. If that's true, you're entitled to that grade. Okay, that's your right. Okay. And when the attempts are very close from one another, As a matter of fact, sometimes I've seen it when the person retakes the quiz, and each time the questions change on him or her, they end up with the same grade. Okay. So what I do in that situation is I regrade all of the attempts. Wherever the highest grade ends, that ends. So it doesn't matter. I can't make that call. It's Canvas that is making that call. So I regraded based on the new attempt, which is slightly different than the first one, and so on and so forth. And based on that, you end up with a grade. In any case, if there is an issue with the grading, whether this quiz or any other exam that we have, and we will have one soon, we need to do it on a one-to-one basis, because I really cannot discuss this in a classroom environment or where there is more than one student involved. And I do not record those sessions, so we go privately on it. You can just shoot me a message and I can do the grading, and then we discuss it afterwards. So this is really the item I want to take from today's discussion, honestly, that regrading is your right, and that it has to be done on an individual basis. Makes sense? For those who are here, you can thumbs up or put a comment. Okay, very good, very good. Okay, having said that, we have quite a few things to cover today. So let me find it first, and then let's close now. And let me switch to a student view. And let me share the screen. Share. No, before I do that, I don't think I have a correct class. Let me first of all refresh the screen. And now I can change to student view. Now I can share the screen. Share the screen. Okay. So we are in Unit 5, Week 5, basically. I mean, not Unit 5, Week 5. And in Week 5, we're going to be covering Units 34 and 35. This is typical stuff now that you have been seeing, the review from the previous week, and the live discussion where the question that I just mentioned need to go in, basically the discussion item in here. And then there is a homework assignment, which I'm going to go to some extent in detail about it, because some of these problems require a little bit of focus. So we need to talk about that homework assignment. It's due on the 25th of September, which is not this Saturday, but the Saturday after. You still have about just under 2 weeks, basically, to finish it. So please take care of it. It's a lot of problems, 5 problems. So you really have to complete that. And then we have this week's objectives, of course. So let me click on those. So this is basically what we will be covering in terms of concepts in the units 34 and 35. This is not the replacement of reading. Okay, this is just basically a summary. So we really are required to know all of these things if we're going to pass any exams or anything like that. This was a discussion item for week 2, I believe, or 3 at most. Okay. So what are the main components of the solar system? Of course, the sun. The sun by far is the main component. It's the center of the solar system. It's what keeps the solar system together. And it's by sheer mass and size, it's actually the biggest player in the solar system. There is no comparison whatsoever. If somebody from another star looking at our region, they will see the sun for sure. Okay. They will look at it probably not too far from here with a naked eye, or probably with even an aided device, they can look at it even from far points in here. So the sun is the main thing in terms of the solar system. And we're going to look into it, and we will see how that looks like. Then in terms of distance of how far they are from the sun, we have these planets, the inner planets first. The inner planets, we have Mercury, Venus, Earth, and Mars in this order. In terms of proximity, of course, you have Mercury, it's smaller in size than all of the others. Then we have Venus, which is the next one in size after the Earth. The Earth is the biggest one in terms of the solar system, inner planets, that is. And then Mars, which is the third planet in terms of size compared to the others. In terms of structure, these are mainly made out of rock and minerals. So these are rocky planets. The density on them is high. It's a very high number, above 3 actually. The case of the Earth, the case of Mercury is above 5 actually. Mercury is the second densest planet in the solar system, just after the Earth. Earth is the densest planet in the solar system. Of course, bigger in density than any of this. All of the four inner planets are more dense than the outer planets. The outer planets are lighter. As a matter of fact, Saturn is even lighter than water. Its density is less than 1 gram per cubic centimeter, meaning if I take Saturn and if I have an ocean big enough to fit it, there is no ocean big enough to fit it, by the way. The Earth is not big enough to have to hold Saturn on it. If there is one, Saturn will float, will not sink, just from the density alone. Jupiter, which is also part of the solar outer planets, is density is slightly higher than 1. It's about the air, that of the air. Okay. As a matter of fact, all of these densities are low compared to those ones in here. Okay. Now these are the outer planets again from distance, from the how far they are from the sun. Closest is Jupiter, followed by Saturn, and then the newer planets that were discovered about 200 years ago. I mean, within the 200 years ago or so, and they are Uranus and Neptune. Neptune is the last planet that we know in terms of the planets. Anything outside of the trajectory of Neptune is called a TNO, Trans-Neptunian object. So all of these objects are in here, with the exception of Ceres, are actually TNOs, Trans-Neptunian objects. These are the dwarf planets. Dwarf planets are still interesting. Pluto, for example, has 5 moons. Eris is a big one too. Sedna has a very, very far, basically eccentric path. Okay. Makemake, Haumea actually is kind of elongated shape. It's really, really spinning so fast on its axis. Its shape is not spherical anymore. It's actually like this, elongated. And then you have far out and far out, and other objects we're going to be talking about. So all of this are the dwarf planets. Ceres is an exception, as I was saying, at least in this list. And I did not list anything else, like Vesta, for example, in the same region as Ceres. Those are smaller dwarf planets. Actually, Ceres is a dwarf planet in its own right. It has spherical shape, and it exists in the asteroid belt, just between where Mars is and where Jupiter is. So these are rocky structures also. Then we have the moons. The moons are actually interesting story also by themselves. All of these outer planets, they have moons. And as a matter of fact, they have rings, all of them. The big famous rings of Saturn are noticeable, but every one of them has rings and have a lot of moons, okay? Jupiter has over 70 moons alone. We know 5 of them that we can name them, basically. Those are the named ones. They are Io, Europa, Callisto, and Ganymede. Those are the 4 moons. Ganymede and Callisto are huge moons. They're much bigger than our moon. And then Saturn, for example, has Titan, and you have all kinds of other moons in here. We're going to talk about them. Mercury has no moons. Venus has none either. Mars has 2 tiny rocks that it captured. They most likely they were actually part of the asteroid belts, and they were captured by it. Phobos and Deimos. Okay, those are the 2 moons of Mars, but they are actually not real moons. Earth is an exception. It has a moon, and for moons sizes, this is actually a very large moon. This is a big moon. So Earth has an odd thing about it going on in here in terms of a lot of things in here. Okay, so Earth has a moon, and it's a very large moon, and we needed to explain how that moon formed. As a matter of fact, we need to explain how the entire solar system formed. Okay, that's another thing that we have to talk about in here. So we're going to talk about that briefly. The path of this, all of these moons and orbits, they're actually governed by Kepler's laws. Remember the first law, the second law, and so on and so forth. And they're characterized by the density. I already mentioned the density several times in here, and it's really the ratio of the mass over volume. And it's measured in kilogram per cubic meter, or most conveniently, actually, we don't use the SI, we use the grams per cubic centimeter. And we say the Earth is 5.5 grams per cubic centimeter, I'm sorry. Meaning if I take a cubic centimeter, where is the ruler? This size, basically this size, and this and that. So basically cube of that from the Earth, it weighs 5.5 grams on average. Okay, obviously you're going to go and get me a rock made out of iron, and you tell me, hey, iron weighs about 8 grams per cubic centimeter. It's double that number, almost double that number. Okay, or lead, which is even more dense. But the point in here is this is an average number, and that is because the Earth is made up of minerals, the ones that you mentioned to me, but it's also made out of rocks, which is silicate-based materials. So this is basically what characterizes the Earth. Mercury is slightly less, and I was saying in here the outer planets, they have less than this. Okay. I didn't mention the asteroids. The asteroids, there are actually two main regions. Three, if you want to call it that. There is the Kuiper Belt. I mean, before I talk about there is the asteroid belt, and that exists between Mars and Jupiter. There is a lot of asteroids in there. Among other things, there is Ceres there and Vesta and other objects in there. So this is one region of extreme heavy density of them. They're everywhere, by the way. If you look at the solar system, you'll find rocks everywhere. But the asteroids, the main group of them, they're actually in the asteroid belt between Mars and Jupiter. And then there is a Kuiper Belt. The Kuiper Belt is just outside of Neptune, and that is actually also has all of the other objects, the rest of the objects plus tinier objects. The structure is different. The asteroid belt is mainly rocky, whereas the other one is made up mainly out of water and carbon-based structure like what do we call them? Methane and also other gases and so on and so forth, frozen because of how far they are from the sun. Okay, so that is the asteroids. Now there is another region that is even further away. In that region, if you look at the all of these objects I mentioned up to this point, including the asteroids, for the main part, they are on the same plane. Okay. Now, in the outer region, all of the objects are very far away from the influence of the sun that they don't really strict. So those are the leftover from the formation of the solar system. They don't stay on the same plane. They're actually in a big sphere, and that is called the Oort cloud. That surrounds the entire solar system, that is. Okay. And comets, actually, they come from the Kuiper Belt, from this region, in a very, very eccentric path. And once they get closer from the sun, they heat up because they mainly have a lot of frozen ice. That ice melts, and when it melts, it develops a tail because of the radiation hitting it from the sun. So that tail will follow it as long as it's within the path of, passes basically Jupiter path. And when it crosses Jupiter path, it's closer enough from the sun to warm up, then it develops that tail. And that's what we see at night for the comets, when we see comets, because we are closer than Jupiter, of course. And then when they get further away, the minute they cross at least just around the path of Jupiter, they freeze again and lose their tail, and they go in the outer regions. So those are the comets. Again, they are visitors from those regions. Okay, so this is in a nutshell the structure of the solar system. How did it come to be? Well, the solar system, according to the leading theory, and I have to really use a word of caution in here in theory, and that is actually a very good point of discussion also. Theory is not an opinion. So you can write it down. For the comment again, item 2 is theory is not an opinion. So when somebody tells you I have a theory, usually they mean I have an opinion. This is what I think, okay? It may be baseless, based on nothing, maybe just a gut feeling about it, okay? That is what we usually talk about when we say theory. In science, though, theory is far more than that. It's a body of knowledge. It's based on observation, based on experimentation, For the case of the sun, we do all kinds of analysis. We, for example, do spectral analysis to see the constitution of the sun. So we do actual measurements, okay? We take, for example, reading about the intensity of the radiation. We take all kinds of things that we measure for the sun, okay? So we do observations and we do educated guesses, which are called hypotheses. And then based on that, we also do predictions, and we go and do measurements. And based on those measurements, we come up with a model. And that model serves to explain all of these observations and actually predict things that it did not exist before. And it goes and verifies them. The collection of all of that work, which spans hundreds of years sometimes, is what a theory is. So it's not an opinion. So it's not like somebody's talking, hey, I have an opinion. No, it's not that. It's based on a lot of, so it's a body of knowledge. That's what it is. It's a collection of a lot of knowledge that is a combination of everything that I mentioned before. So this is a good item to mention in here because it's very important. So the theory in here is the following. There must have existed previous stars in our neighborhood. Among other things, there was supernovae in this region. And that supernovae is what explains the iron, for example, on Earth and all of the heavy metals everywhere in the solar system. So you have a cloud of molecules, basically, a three-dimensional cloud, like you have a dough, for example. And but because of a gravity, the materials are attracted to one another. So once a material attracts one another, it loses potential energy and gains kinetic energy. Remember, the potential energy is inversely proportional to the distance, but it's a negative number. So if it increases in magnitude, it goes down in overall. So it goes down, then the object speed up. Similar to the example of the rubber duck or rubber ducky in the bathtub, okay? So if the bathtub, you unplug the thing or you turn it off, the water starts to spin and go down. So if you put a rubber ducky, it's going to spin far away slow. And as it gets closer, it's going to gain more and more speed, okay? That is in a sense similar to that because it gets closer, so it has to gain kinetic energy. Once it gains kinetic energy, its temperature rises, goes up and up and up. Because the sun started in the process and sits in the middle of the solar system where it was forming at that time, it gained a lot of material, which is mainly hydrogen and helium, plus some traces of other elements, as I mentioned before, iron among them and all of the other elements that makes us and everything else on Earth. So the main two elements are hydrogen and helium, and as these elements start to get closer and closer, their temperature rises further and further. The temperature gets in the millions of degrees, as a matter of fact. This phenomenon started in a sense with more in the center with more intensity, but it happened also somewhere else in the solar system, like Jupiter also started collecting a lot of those materials soon after the sun did. And after Jupiter, Saturn most likely started to collect. So the early arrivals, the earlier you get in, the more material you gather, okay? So now at this point, the sun has very high, the center of the solar system is extremely high, but did not go nuclear yet. No nuclear reaction happened yet. You need a high pressure. Because the material was getting in a high concentration, so the pressure increased and the temperature increased, and those are the conditions for nuclear reactions. The minute it reached a certain point, the core of the sun went nuclear, basically, okay? Now the sun started to collapse on itself because of the heavy weight of the gravity, but the nuclear reaction prevents the collapse completely. So there is a balance that was struck. When it went nuclear, immediately all of the materials that were in the solar system were ejected from the immediate neighborhood because of the radiation that was pushed in every which way direction, which stopped the rest of the planets from growing any further from more materials because the materials were gone. So that's why Jupiter did not go nuclear. If the sun did not go nuclear too soon, most likely what happened to Jupiter also, it would have gone nuclear because it would have collected more and more of those hydrogen and helium mainly, which is the main structure of Jupiter. And then also it would have its temperature would have been high enough and its pressure would have been high enough for it to become nuclear and be another star in our neighborhood. But what happened is when the sun went nuclear, basically it starved all of the other planets from more materials to grow any further. And basically the solar system was at that point. Now, why is everything on the same plane at that point? Well, the reason why is because as they are coming closer and closer, the angular momentum must be a conserved quantity because there is nobody pushing these materials together. They are doing it on their own. So as they get closer and closer, they flatten because the angular momentum is actually a vector and its quantity needs to stay the same. So everybody stays on the same plane for the most part. And the reason why they speed up is actually the angular momentum in magnitude also is the one that keeps them faster and faster, which raises the temperature. So there is everything now is in there in terms of how this is how the model for the solar system has formed. Okay. And again, it is very well documented by the structure of this objects, by the age, by everything that we have. How do we measure the age? One of the ways of doing the age is, for example, using the beta decay or the decay in general, radioactive decay in general. Materials that have a very high energy inside their nucleus, they want to go stable. They want to become more and more stable. So they lose that excess energy. They lose it in the form of radioactive materials. So that is a natural phenomenon that happens everywhere. So this is actually one of the forces of nature that we know of, which is actually the third force of nature, which is the so-called weak nuclear force. Potassium, for example, is a good example that you can use it to date any material that it has. So this is what potassium undergoes to. Two possibilities. One, for the mass majority of the times, 89% of the times, potassium isotope 40, which has actually 19 protons in it. That is what potassium is, 19 protons. And 21 for this isotope has 21 neutrons. Total 21 plus 19 is 40 inside the nucleus. Okay. Obviously, if potassium is a neutral atom, it has also 19 electrons. 19 electrons in the structure, you have 18 that are neutral, strongly tied to the nucleus, and 1 electron that participates in chemical reactions. We call this one the valence of potassium, which is similar to that of hydrogen, the entire line. Lithium and sodium, they are actually in the same line, okay? Now, in the periodic table, if you have had a chance to look at it. So, potassium, I'm talking about the nucleus. We're not talking about what's going on in the outer shell. We're not talking about chemistry. We're talking about nuclear properties now. So, has two possibilities. Either it loses an electron, converting one of its protons, one of its neutrons, one of the 21 neutrons into a proton, making the number of protons instead of 19, 20. Now we went up by 1. Of course, reducing the number of neutrons from 21 down to 20. You will have 20 plus 20 is still 40. But now the element is completely different. It's no longer potassium any longer. It's calcium, actually. Calcium has the number of protons in it 20 by ejecting an electron. Obviously, there is another thing that we need to make this equation right, and that is actually neutrino. To be more specific, it's an antineutrino. Antineutrinos, or neutrinos in general, is a very interesting subject by itself. We'll be probably talking about them down the road to help us understand what's going on inside the sun itself, okay? They're extremely light particles for the most part. And they are actually don't have a charge, hence the name neutrino. Neutrino is the little, the tiny one that does not have a charge really. And like the neutrons, which are bigger, they don't have a charge too. And they come in different flavors actually, okay? So this is, forget about the neutrinos, forget even about the electron that is ejected. Just focus on the potassium going into calcium with a probability of 90% for the most, 89% to be more specific, okay? 11% of the times, the potassium does not do that. The potassium actually captures an electron. When it captures an electron, that electron will combine with a proton so that the charge cancels. And now instead of having 19 protons, I will only have 18 protons. Obviously, the proton that captured that electron becomes a neutron. And instead of having 21 neutrons in it, I have 22 neutrons in it. 22 plus 18, it's still 40. That element is actually a noble gas. It's the argon. Plus, again, another of those things, neutrinos. Forget about them. An argon. And an argon is actually neutral and noble gas. It does not interact with anything. Here is the deal. If I have a sample rock, okay, or a sample in general, and I can determine somehow how much calcium it has versus how much potassium it has, and versus if I can access even to the argon, how much argon it has, okay? I can tell the age of that rock, how old it is, based on the radioactive properties, on the half-life of the potassium in this case. For this process and for that process, I can determine how old it is. It's amazing stuff to do and how to determine. So this is in a sense some of the studies we use to determine this thing. So it's again, it's not just a theory based on opinion, it's based on research and actually data collected and observations and spectral analysis to study this light basically that is coming from, emitted from there, to see what's in there. Because how am I going to know, for example, a rock, if I don't have it in my hand, what its structure? Then in this case, probably I will just study if light passes through it, is there light that is absorbed or something like that. This is what we do, at least for the stars, okay? Or for the clouds in general, okay? This is the Nebula Theory, I mentioned it already. And the materials, if you look at, for example, the structure of the Earth, and this is what we believe is happening everywhere, is usually the materials that are a lot denser, they sink in. Hence, that's the core of the Earth that is made mainly out of nickel and iron because of the fact that it has all of that. So it went inside. For the most part, that is where the iron is. There is a very small quantity of proportion of that that's sitting on the mantle and all of other places of the Earth. Anyway, this is basically what these units are. I hope that you guys, this is not a replacement for reading these units, but rather it's for a for you guys to like a summary. Okay, I have my laptop in here, so I'm going to pick up the mouse in here, and if I can find where the mouse is working, and I'm going to share something from here that hopefully will give you a much better visual of these things. So let me find it first of all. It's complaining I have an outdated version because I did not update it in 3 months, but that's fine. The reason why I have it on my laptop and don't have it on my computer, first of all, there is a big hum from it that is coming because of the fact that it uses a lot of the power from the computer. Let me pause it. And let me, can I minimize this in here? Really should not have done that. Can I? Trying to go into the find the share button now. Let me share this universe inbox. If you have access to a computer with good video card, this is actually a very good simulation to have because it has a lot of physics in it. It has a lot of simulations in it. Let me X this one here. And you can simulate a lot of the things for the solar system, for the stars, for the galaxies, and you can do all kinds of things with it, okay? So here is a look at the solar system from far away. Obviously, the biggest thing in here in the solar system is the sun, as I mentioned before. So let me zoom in onto it to see how it looks like. The sun, for the most part, trying to zoom, okay? Sometimes when I zoom, I touch the key. So for the most part, hopefully it's not too bright for your eyes. Maybe you need to move out a little. Okay. So for the most part, like I said before, it's mainly hydrogen and helium. Can I use the keyboard in here and put them in this thing? Let's see if I can use the mouse directly on the screen. Okay. So for the most part, the sun is mainly hydrogen, and actually, as a matter of fact, I can look more into the properties in here and see the sun. Of course, it uses the sizes and the properties of the sun. One solar radius is about 717,000 kilometers. Okay, So its surface temperature is a little over 5,700 Kelvin. So it has a lot of useful properties in here, okay? So this is the center of the solar system. Inside of it, inside the core, there's nuclear reactions that are happening by combining the different protons, basically here, hydrogen. Hydrogen, ionized hydrogen. It's not really hydrogen. So when I say hydrogen, it's really in the proton form because it's too hot for hydrogen molecule to exist. I mean, the electron is stripped out of from the hydrogen atom. From even the atom itself, let alone the molecule, not H2, forget about that. H itself does not exist in these high temperatures. So it's protons, really 4 protons, they combine to give you the alpha particle, which is really the helium in this case. So this is what's happening in the core. And then there is a region, we're going to get into more details about the structure of the sun. There is a region of convection region where there is actually the gases, which is really mainly hydrogen in this case and helium mixtures. They're actually going into like a transition, and the photon that is formed, the light that is formed, the energy of light that is formed inside the core will need to go through the core first, and then through the convection zone, and then through the thin layer, which is what we see, okay, of the sun. It takes about 100,000 years for light to escape the sun. So if there is a nuclear reaction right now that happens, that light will not be seen on Earth until about 100,000 years from today. The light that we see right now from the sun, if you go out and look at it, that happened about 100,000 years ago. When I was talking earlier about neutrinos, the neutrinos that hit us from the sun, they happened only about 8 minutes ago. That's why actually neutrinos are far more useful to tell us about what's going on inside the sun than the light itself. Because if something happened to the core today, we will not know it in terms of light until 100,000 years later. But we will know it in about 8 minutes based on the neutrinos that are hitting us from every which way. So neutrinos are a byproduct of this process. And also they tell us about what's going on inside the sun. So this is what we know about the model for the sun. This is why we know what we know, because of these studies, because we have neutrino detectors now that we can use. One of them is actually in Canada, and another one is actually in Japan, and we have others somewhere else. We have the Kamiokande in Japan, and we have all kinds of ways of knowing this thing. So the sun is by far the most important object in the solar system. Okay, let me try to zoom out. Because when I touch the keypad, it angles itself, and then when it does, it gives me this thing instead of zooming out, zooms in, which is really not what I want. So let me go back now and find Mercury. Mercury, the properties of it. Let me zoom on it. This is the closest object to the sun, and let me look at it from the lit side. Basically put the sun behind me and look at it, okay? As you can clearly see, it has this cratered surface that is made of, it has the characteristics of a lot of craters in here. And these craters are remnants of what happened to the entire solar system when it was formed. Initially, because there was a lot of debris left over from the material that was in the solar system. Not everything was ejected, by the way, by the radiation when the sun went nuclear. The heavy ones were not ejected, they stayed in, like the planets, for example, and even lighter objects in those. So those, they went through a heavy period of bombardment, basically, where they basically collided with the bigger ones. And you can see the evidence of it when you look at the moon, for example, because the moon did not have a lot of atmosphere to begin with. So everything that is in there for today that you see is from this activity that happened early on, okay, and later. The same thing is true also for Mercury too. Mercury also has all of these craters. As a matter of fact, if you look at the moons of Jupiter, like Callisto and Ganymede, also they have this structure because of the fact that they did not have a lot of atmosphere, and or they did not even have a geology on their surface. Like, for example, the Earth or Venus, they had a lot of chance to resurface and change the surface, so you don't see a lot of this ones on them. Same thing, for example, for Io. On the surface of Io, which is a moon near Jupiter, it is a lot of activity also in there too. So that's why you don't see a lot of these ones on its surface. But the bigger craters, they are there. And as a matter of fact, there is one big one not too far from here, which is in Arizona. Anyway, so this is the surface of Mercury. It's mainly metallic. As a matter of fact, the core is very, very large for it compared to the size of the planet. And the planet is, as I was saying, is very close from the sun. As a matter of fact, it's about 0.30 astronomical units. So let me zoom out and find Venus, which is the next object. Come on. Okay, here is Venus. And let me zoom in. Venus, no matter how far you zoom in, you're not going to see much details on it. Now, since we are in this angle, so we really have to change the location in here and put the sun behind us. And you can see in the background the Milky Way. You can't see much on Venus because it has a very super thick atmosphere on it that really prevents anything you can see. It has, a matter of fact, the pressure on Venus is about almost 100 times that of the Earth, because of the super thick atmosphere. The atmosphere of Venus is mainly carbon dioxide and sulfuric acid, and it's really very, very hot, very dense in terms of the high pressure, very much high temperatures, and extremely toxic for any living form that we know of. It must have had water as recent as about 150 million years ago, but that water, because of the extreme high temperatures, must have dissolved, and the oxygen went by its way and probably recombined with the carbon to form carbon dioxide. And with the hydrogen being super light, but because of the high temperatures, because of the super light, so it went up in the atmosphere. And because of the extreme heat, it gained a lot of kinetic energy and must have escaped the planet. That's what happened to the planet. So it's really a very, very bad place to be in. And it's probably a greenhouse effect that went completely all right, since I see Earth in here, let me zoom on it. That's the next object. And the Earth is it's a nice temperature when the water is actually in liquid form. And at this point, it's really a jewel in the solar system, okay? It has a thick enough atmosphere, not too thick like Mars, like Venus is, but not too light like Venus does. Its atmosphere has, of course, carbon dioxide, but mainly it's really nitrogen. That's the main component in the atmosphere of Earth, similar to Titan. It has oxygen, which is a high concentration in terms of the planet, but it's mainly on the surface, really. And as you go up and up, the high oxygen starts to become less and less. And that is because of the fact that the living organism made it, for the most part, okay? So this is really the planet itself in here, and it has high geological activity on its surface because of the fact that it's massive enough so that it has actually heat inside its core, and the heat is coming actually from radioactivity actually in it. So that is really the story of the Earth. Okay, we're going to get into more details about this one. What is Mars? Let me find
Professor.
Yes.
Is this in real time?
This is this is actually, no, I'm sorry. This is not Stellarium. Stellarium is in real time. It's actually simulated. And you can go actually in the future, you can simulate things with this one. So this is actually a simulation software, okay? But it gives you actually a lot of details. If you look, for example, at the Earth in here, it gives you all kinds of details about the temperature, and you can actually model things with the Earth. You can put it closer to the sun or further away, or add the concentration of something, and you see the temperature, average temperature going up and down. So you can really study and simulate things of what happened to a certain planet or a certain object to see what that object will do. So this is actually a very nice one, and it's really uses physics, by the way. It uses a lot of science in it, in other words, okay? So it's not a far-fetched story from what it needs to be. Now I need to find where Mars is, and here is Mars. So if I bring Mars into view, into the center, I'm sorry, so that I can zoom on it. as I was saying, Mars has a nice features in a sense that it has two moons. It's a smaller object than the Earth and Venus. That's why it lost a lot of, it did not have a lot of radioactivity compared to the Earth and Venus. That's why it lost a lot of its geology. And in doing so, it lost its magnetism, which means that its atmosphere was lost to the because of the solar radiation its atmosphere was lost for the most part. It has a lot of carbon dioxide in its atmosphere. It has basically, this is the structure for Mars. Mars is an interesting object for us as humans and interests us a lot. I mean, first of all, its geology is an interesting one. It has canyons that are much, much larger than our canyon. It has mountains that are much larger than our mountain. And I mean by it specifically, Mount Olympus, Olympus Mount. Where is it? It's in here probably because of the day-night in here again shift. Okay, so probably if I let the time evolve a little, I may be able to allow it to spin enough so that we can see the mountains. But the big Mount Olympus Mount is a big mountain. As a matter of fact, it's much taller than any mountain on Earth. But it's also much bigger in area. It's the size of France, okay? Big states in the United States. Meaning that if you're climbing the mountain, you wouldn't even think that you are. You think that you're climbing you're walking basically, if you can, of course, provided you can breathe the atmosphere or do something about it. But the thing with it, it's not as steep as you might think. I mean, it's very, very gentle because of the size. It's a huge mountain. So the structure itself is interesting. We've sent so many missions to Mars, the latest of which is Perseverance. Perseverance has a nice component to it, which was Ingenuity. We sent it in February 18th of this year, by the way. Ingenuity is a drone that flies off of the surface of Mars. And initially, we were not sure if we have the proper technology to really do that because of the density. We did not really, the low density for the atmosphere. You really, for the blades to work correctly, you really need to have a high enough density so that they have a lift. But we were able to successfully do a lot of missions with this one, which opened the door for a new era of space exploration. Now, because the follow-up to Perseverance, which is the rover on that took Ingenuity there, was supposed to collect samples from the surface of Mars, and those samples, they were going to be dropped as Perseverance is moving. And later on in 2027, we're sending another mission actually, so that we can go and collect those samples. The plan initially was, we have a lander. That lander will go and move on the surface and collect those samples and put them in a capsule and send the capsule with a proper proportion, which is something that we need to test. And one of the things Perseverance is doing is actually making oxygen on the surface, because we need that oxygen for the proportion of this rocket once in 27. So the thing is, the oxygen now that is following the Perseverance, we go and collect those samples, put them on the rocket, and send the rocket to the orbit, the orbiter that will remain around Jupiter, around Mars, and then that orbiter will bring the samples back to Earth so that we can study them in the laboratory here. But the plan now they're thinking to change it. Why? Because we know how to fly things on the surface because of Ingenuity. So instead of having a rover now, NASA is thinking instead to have actually like a drone, since we master the technology, much bigger drone now, to collect those samples and then fly them out or send a rocket from the drone or something to the orbiter so that we can bring them to Earth. You see, now we're transitioning toward a new thing. Because of the success of Ingenuity, actually, the Chinese are coming up with a different plan. Initially, they had actually a drone proposal a long time ago, actually before NASA did. But now they're actually trying to have even a fixed wing planes flying over the surface of Mars. And those, they can span hundreds of kilometers and give us an overview and study that is much, much deeper than what we know. So the future really is changing in terms of space exploration based on successes from this year. Now, NASA also is planning another mission to Titan, which is one of the moons of Saturn. And Titan has a very thick atmosphere. Actually, it's about 1.5 times that of the Earth. It's mainly basically nitrogen and all of these elements, similar to the Earth actually in terms of nitrogen, because we have mainly nitrogen in our atmosphere. So now probably Titan, the mission is going to be completely a flown mission. I mean, so this is basically some of the things that we're learning as we're happening. This is fresh from the oven. This is basically papers and studies that are current right now about this one. Now, if I move further away from Mars and leave Mars behind, and as you can see, these dots in here that you see them are paths. As a matter of fact, this is Ceres. Ceres is dwarf planet. I can zoom on it and you will see that it has a spherical shape, okay? You see Eris in here, but Eris, don't be fooled by the simulation, it's far away. And I can show you what, even in the simulation, this is very far away. So this is Ceres. Ceres is an interesting thing. It has two white dots that are of interest to us in here, because is it water, is it frozen ice? So Ceres is an interesting object that we study extensively also, and there is actually a mission trying to go in the future for it, thinking that maybe it has also an underneath ocean that could harbor life as we know it. Ceres is actually a dwarf planet that exists between Mars and Jupiter, okay, and it's part of the asteroid belt. The Japanese actually had a lander on another asteroid in the region, okay? Now, after that comes, of course, Jupiter, the big boy in the neighborhood. Okay, Jupiter by far is the biggest object in the solar system after the sun, and it has 70 some odd moons. The four of them that are known are, of course, Io, Callisto, Ganymede. I'm looking at it from the polar cap. Let me look at it from a different angle in here. That's probably what happened to the other one. Okay, so this is it has rings, it has all kinds of moons. It's really a fascinating object, and we're going to get into its details. It's mainly hydrogen and helium, by the way, including a core that is mainly probably metallic helium. I mean, metallic hydrogen, which is something that is weird. I mean, if you think about it. Then after Jupiter, of course, comes Saturn with its famous rings. It's going to look similar to Jupiter in terms of its layered structure because of the high atmosphere and the extreme high winds that it has in its surface. And the rings also. The rings is the main feature that is known for Saturn, but all of the outer planets, including Uranus, which has this bluish color, including also that of Neptune, they have this bluish color because of the high methane concentration in their atmosphere, okay? So I'm zooming in on Neptune, the last planet in the solar system. And it has this bluish, it's actually darker blue than the other one is actually more like a greenish color, I would say, because of this structure in here. And this is the polar caps. And the density is slightly higher for both Uranus and Neptune than that of Mars and that of Jupiter and Saturn. Those are the planets, okay? Now, if I zoom out, anything outside of the planet, Neptune is called a TNO, including Pluto, by the way, which is an interesting object by itself. So if you zoom on it, it gives you a real view of the thing. And I can change the view, but I really don't want to change it. It gives you either a realistic view or if you do give it a realistic view, you're not going to see much, okay? Because they're dark objects. Or basically an enhanced view. We can see in the background, this is Pluto. Pluto is an interesting object because it has a big moon. It's actually the ratio of a moon to planet. It's the biggest one between Charon and Pluto. And it has actually 5 moons or so. So it has actually, it's because it's an outer project. The fact that it's a dwarf planet is not less interesting than any planet. As a matter of fact, there's a lot of interesting studies going on. Pluto is not the biggest of them all in terms of the TNOs, the trans-Neptunian object. It's actually Eris is. Eris is a dwarf planet also in this neighborhood, but it's further away than Pluto. That's why we didn't discover it to begin with. And we didn't discover it until later. Let me find it first. Okay, where is it? Do I see it in here? Here it is, very far away, but it's bigger than Pluto is. Of course, we have other objects. This is not it. We have Sedna. Sedna is an interesting object that is a very, very, first of all, it's very far. And second, it's actually, it has a very eccentric orbit that takes it very far away from Pluto. At this point, look at where is Earth? You cannot even read the writing on it. It's really not even there, or even Jupiter for that matter. We are outside, we are very much in the Kuiper Belt right now, okay? Look at how the orbit of Sedna. At some point, we're lucky enough to have it right now close, but not too close. As a matter of fact, very far. But at some point in the future, it's going to be even further away. So we have Sedna, we have Haumea. Haumea has this very weird structure, as I was saying. If you look at it, it has this egg shape. Actually, it's very eggy shape, because it's spinning so fast on its axis. It's not sphere anymore. It's actually, it has this elongated shape in here. So this is an introduction to the objects in the solar system. Far away, of course, you're not going to see anything. You're going to hardly see the sun. This is the solar system. Oops, I'm still zooming in on Pluto. I don't mean to do that. Let me put it on the sun. I'm using the mouse, and because of the large Kuiper, which is another one of the which is a dwarf planet, Haumea, Makemake. I mentioned a few of them in here. And let me see here. And now we're zoomed in on the sun. So this is how the solar system would look like from the vantage point of very far away. Nothing at all other than the sun. Maybe if you're lucky enough, you can see Jupiter or Saturn. Okay, so let alone all of the other tiny objects. So this is in terms of the structure of the solar system. Let me exit this program. Let me first of all stop sharing. I can find my laptop again. And we're going to talk about something interesting in here. So again, this is not, so I'm going to exit this computer in here because I really don't need it anymore. Before I do that, let me close this program. Okay. Let me go back into with you guys to the screen where I was before. Share. So that to see what we have. Again, we are in week 5. These are the objectives for the week. Let me go back into the models. Please do read that we have 2 items today that we discussed. The first one has to do with the grading, which is your right. And please let me know on a one-to-one basis. And the second item, now it's about the theory. Okay, theory is not an opinion. Okay. So we have this assignment in here, the homework. Let me click on it, which is due the 25th. So we still have about 2 weeks, less than 2 weeks to finish it, but it should be plenty of time to do it. So I'm going to talk about this one. Again, when I submit this one, let me start the assignment. I'm a student, of course. I'm in the mode of, I'm looking at it from the vantage point of a student. So this is how it looks like to you. 2 ways of answering this one. I would do text entry in here. I could do that. But I would say, for example, problem 10, I really have to be very specific, and then I put my answers in here. Try to show my work. If I have to do an equation, there is this nice tool in here. If you're familiar with it, that's great. If not, it's a good tool to be familiar with it. It's called Insert Math. So you click on it, and it takes you to this view. In this view, you can do simple stuff. Like, for example, if I want to do fraction, mass over volume. Okay, that is the same thing. Or if I want to do the cubic root, for example, I put a 3 in here, and let's say, for example, I put 27 in here. Okay, so this is how we can do things in here. Of course, there's other things in here that you can do: multiply, you can do equal. Those are the main things that probably we're going to be using: the cubics and the ratios and multiplications and additions and things like this one. The reason I'm showing you this is so that you know that you can do this. You don't have to. There is another way of doing it that is familiar with people, and that is to use this symbol area, mass over volume. This is actually would work too. And if I want to do the cubic root of 27, there is actually another way of saying it. I can say parentheses 27, and then I use the caret. This is called the caret symbol to any power. If it's the power 3, I put the 3 there. If it's the power, if it's to the cubic root, if you're familiar with the algebra, it's 1/3. That is what the cubic root is. So this is, in a sense, similar to this language. If you're familiar with the insert equations from this menu, that would be great. If you're not, then you can use the common convention that people are using, and you can basically have that, okay? If you're too advanced and you would want to use something even fancier than this, you switch this mode to the advanced mode, and that mode actually takes you into so-called LaTeX representation. If you're not too familiar with LaTeX, ignore this. So you can use the programming aspect of it, and you can use stuff that is, for example, like this, okay? Mass, and you're entering in mass in here, and it should give me the same thing in here. So it's going to be a mass over text, which is volume. I'm just showing you this. If you're familiar with it, you're good. If you're not, this is actually something, especially if you're going to major in something has related to science and math, this is something good to know. If you're not, ignore this. It's similar to the basic mode that I was showing you. But this is more of a programming aspect of it. So I could do it this way, or what did I do earlier? I did cubic root. So I could do, for example, I forgot. How do you do cubic root? Is it root? No, SQRT. I don't know if this is going to work or not. Yeah, this is the one, for example, of 27. So this is the notation that is actually used also in the programming language of it. So if you're R, that's fine. If you're not, you have two other options that you could do. This is similar to that, okay? So this is the basic actually equation. And this is just mass / volume. Works fine, good. You're not going to lose any points. As a matter of fact, it's good enough for this. Or you can use the caret and the combination of symbols and things like that to represent the same thing. So you have all kinds of options to do it this way. Now, if you don't want to do the text entry, which is fine, then you can do another way, and that is the file upload. You do it on a piece of paper and upload the image. Make sure the image is clear though. Okay, take it with your phone, or work it on a Word document and upload the Word document. However you want to do it, okay? So you have too many ways of doing this. Those are the two ways that are, please do not do Dropbox or Google Drive or Office 365 maybe, because that means I have to log in with my credentials, my personal credentials to your personal account. And that is not good for the college, because they probably would want to have an audit at some point, and we would want things to be contained within the accounts of the college. So I recommend that we strictly use either Office 365 if we have to, or upload the files. This is the ideal, or do a text entry. This is the ideal. Those are the two great ways of doing business. Canvas is giving you all of this. Do not use them, including this one, by the way. I'm not really too great about it, okay? So try to restrict yourself to one of these two. So let's look at these problems now. Let's do them one at a time, at least to have a feel of what they are, so that we can do them. So I'm gonna stop sharing this screen, and I'm gonna share with you another screen now. And that screen is where we're going to talk about these problems individually, each and every one of these problems. For that, I need to put them on one side of the screen so that they can see them. So I'm going to put them on this screen. Am I still sharing the OneNote?
Yeah, it's on.
Okay, very good. Okay, very good. So that because I moved so many things on screen, I don't want to. Okay, so we have problem 10, 11, 12, 13, and 14. So there are 5 problems from 10 to 14. Okay. So the first one, 10, talks about series. It says that series has a period P of 4.60 years. Okay. And What is its semi-major axis? A. And where is it in the solar system? So 4.6 years. Well, if I use Kepler's law said p squared is equal to a cubed. I know p. I can find what a is from this equation. P is 4.6. When I multiply 4.6 times 4.6, this must be a cubed according to the third law of Kepler. Well, 4.6 times 4.6 according to my calculator times 4.60, not 4. It's the same thing. It's going to be 21.16. This is no good. This is not correct. Let me tell you why. This has a number that is important called the significant figure, which is 4. Has a number that is important called significant figure, that is 6. Has an important number that is 0. Why is it important? Because it's after the decimal points, and the zeros after this point become significant. So it has 3 significant zeros, and this one also 3 significant zeros, and the answer has more than what we started with. This is no good. We have to really restrict our answer only to 3 significant figures. The calculator doesn't know, thinks that you know these numbers with an infinite accuracy, but you don't. You know them only with this many accuracy. So you need to bring back your answer to a tamed way. So you know the 2 is significant, you know the 1 is significant, and you know this one is significant. Is it really a 1? That is the question. For that, you ask yourself, is this number 5 or more? The answer, yes, it is 5 or more. As a matter of fact, it's 6. This is the first number that is not significant. You ask yourself that question, is it 5 or more? If it is 5 or more, then you round it up. What this means is you add 1 in here. So when I add 1 to 1, it becomes a 2. And then the rest does not change because I don't have to carry anything in here. So it's 21.1. This is a cube. So this is how you proceed about this kind of things. In science, you have to be accurate. Since we're doing astronomy, we really have to be accurate about these things. We cannot really invent something. This is as if you have more accurate answer than what you started with. This is impossible. This is what you measured. You cannot be more accurate than what you measured. This is what this thing is. This is why it's important. It has to do with integrity, as a matter of fact, because yes, you're claiming more accuracy than what you really are. This is what you are. You know for sure 21.2. That's because the 2 is not really correct. Same thing with the 0 is actually not correct. Okay, the 0 is actually, there is an iffy thing about it. So you cannot tell me that you're iffy about this digit because you're not. Okay. I'm going to use a calculator. So let me show you how I'm going to use a calculator to find the cubic root, because the cubic root is kind of a little bit of work. So if you have a calculator, that's good. That has a cubic root. If not, then you really need to do some work to get the cubic root. Okay. Okay, let's do it first. Okay. The cubic root, it's first of all, 21.2. We usually raise it to the power. I was showing earlier that it's 1/3. That is what the cubic root is, to the power of 1/3. So if I do this number according to this calculator, again, it gave me this whole bunch of numbers, which are not accurate. I need to really retain the 3 sig figs of them, which is the 2 and the 7 and the 6. Those are the significant figures. The question I need to ask is this 7 more than or equal to 5? And the answer, yes, it is actually more than or equal to 5, because it is more than 5. It is 7, actually. Since it's more than or equal to 5, I need to round it up, meaning I have to add 1 to this 6, and it becomes 2.77. And that's it. That's the answer. So the A then, let me stop sharing the screen in here and share. The A then is 2.77. That is the semi-major axis for this series. Okay, let me talk a little bit about this number. If I cube the 2, that means 2 times 2 times 2. This is 8, because 2 times 2 is 4 times 2 is 8. Now, if I go higher than this number, which is 3, well, the cube of 3 is 3 times 3 times 3. 3 times 3 is 9 times 3 is 27. It's more than 21.2. That's why the answer is between 2 and 3, because the cube of 2 is less than 21.8, 21.2, and the cube of 3 is actually more than this number. So that's why the answer is between the two. So sometimes you don't have access to a calculator, but you can estimate things. I know the answer for the cubic root of 21.2 has better be more than 2 and better be less than 3. Probably a guess is 2.5. Okay, that's a number between 2 and 3. That's why it's a good idea to check these things to see if they make sense. Here is where it lays. I know Mars is 1.5 AU, 1.52 AU. This is the answer, by the way, is in astronomical units. And I know Jupiter is 5.20 AU. This number is more than 1.52, but less than 5.2. So Ceres is probably here. As a matter of fact, 3, somewhere in between, actually, like here. Okay, so this is where Ceres is. And it's 2.77 astronomical units. Just as what we did earlier in the simulation, that it appears it belongs to the asteroid belt, and the asteroid belt is really between Mars and Jupiter. So that is the first problem. I did it in somewhat detail because I want you to really have a feel for it. And it's still you're responsible to submit it because, again, homework is not an exam. Homework is not a challenge in the sense that I want you to really do these numbers to have a feel for them. I did the simulation earlier, but now when we do the numbers, it makes sense because 2.77 is more than 1.52 and it's less than 5.20. So you know where Ceres is. Okay, this is what the point of this exercise is. Let's look at problem 11 now. For problem 11, let me find 11 first of all. 11, it says Sedna, an object in the outer system, has a semi-major axis of 520. So Sedna, remember Sedna, I showed it very far away, has an astronomical an A, which is the semi-major axis of 526 astronomical units. What is its orbital period? Basically, what is P? How long does it take for it to go once around the sun? And then also remember that Pluto takes 248 years to go once around the sun. So this is Pluto. They want you to compare this number to that. So what you do in this case is similar to the other problem, except now you know what A is. So you take A cubed, and A cubed is 526 times 526 times 526. This should be P squared. You plug it on this calculator, in your calculator, and you'll find that the square root of this number, because that's what P is, needs to be the square root of 526 times 526 times 526. The answer should be about 12,000. You need to do this. It's more than 12,000, okay? Slightly more than 12,000. You need to do the math in here, okay? 12,000 is much bigger than 248 years. So the last time Sedna was in this position was way back in before even Moses. Moses was what, 5,000 years or so? Okay. So this is a long, long time ago, before the pharaohs, before the Babylonians. So it's a long, long time ago. Probably around the Babylonians' time, I don't know. No, it's actually before that. 12,000 years ago is a long, long, long time. When Sedna was in this position, that's why it's a very, very eccentric path. Right now, it's close by the sun, relatively speaking, but it's still way further than Pluto and Eris, and yet at some points it's going to be even possibly further. Okay, just to show you how far it is compared to 248 years. Last time Pluto was in this position was about 2.5 centuries ago, which puts it around the Civil War in the United States. Okay, so this is some of the questions in here. Question 12. It says, suppose you have an asteroid that with an orbit that brings it as close as 0.5 AU. So here is the sun again. Here is where Mercury is, which is 0.4, roughly. This brings it to 0.5, very close. Remember, Venus is here, 0.72. So this is actually very close from Mercury. And then at some other times, it brings it to 5.5. Remember, Jupiter is here, which is 5.2. So this is Jupiter. So at some point in its path, it's here at 5.5 AU. So this is its path. This has a major axis, not semi-major axis, this distance, which is 5.5 plus 0.5. That should be 2a. 2a must be 5.5 plus 0.5, which is 6. That means a itself is half of 6, which is 3 AU. Now, what is the semi-major axis? The semi-major axis, I already answered it. What is its period? Now, all you have to do is take p squared and make it equal to 3 cubed, which is 3 times 3 times 3, which is 27. Okay? And now all you have to do is take the root of 27, and that is should be around 5 years or something, because square root of 27 is slightly more than 5. So it's going to be 5 years and some change. You need to find it, okay? That's part of your answer in here. So this is 12. Let me talk about 13 now. Again, it's a good idea to work in teams. And if you can't, please ask me questions if these things are not clear, or if you have a difficulty with it, so that we can make sure that you guys, especially depending on your background in math, that's going to be the problem. It says if a comet orbits the sun and reaches 1 AU at its closest approach to the sun, and its orbital period is 27 years, what is its maximum distance from the sun? Here is an object. So here is the sun, by the way. Here is where the Earth is. So at some point, it's the same orbit. It doesn't mean that it's on the Earth, because the orbit of Earth is a big circle, so it could be anywhere on that orbit. So this is at some point, it's 1 AU. And at some other point, it's at a distance x. We don't know. I know that x plus 1 must be equal to 2a. Okay, I don't know what a is. Well, a, I can find it from this equation. I know that they tell me that its orbital period is 27 years. I can square this number and equate it to a cubed. From here, I can find what a is. A should be about what? 9 AU. Do the math, please verify, check. All you have to do is square 27 and take its cubic root. Well, the cubic root of 27 is 3 by itself. So when you square 3 times 3 is 9. It should be correct, okay? But check it, verify it, okay? So A is 9 AU, and 2A is 18. 2 times 9 is 18. 18 deduct from it 1. This distance should be 17 AU. So its closest approach is 1 AU, and its furthest approach is, furthest point is going to be 17 astronomical units. That is 13. Please verify. I'm not saying the numbers are correct. So you need to check these things and make sure it's working. And finally, and I think we're running out of time, calculate the speed in kilometers per second. This one needs a lot of conversions in here, 14. They gave us a circular orbit. So the object, an asteroid, goes on a circle of radius, which is a, is the radius in this case, because it's a circle, 4 AU. And they want to know its speed in kilometers per second. Well, the speed is going to be the circumference, which is this whole distance. And this whole distance is traveled in one period, p. So it's going to be the circumference divided by p. So I need to find p first. For me, p satisfies the equation p squared is equal to a cubed, where p is just the cubic root of this number. So in this case, p is just the square root of 4 cubed, okay? Well, the square root of 4 is what? 2 to the power 2. So 2 cubed is going to be 8. So it's going to be about 8 years. Okay, please verify this. I'm not sure. Okay, not sure. I'm just basically guesstimating at this point because you'd have to check. You have to do the algebra. Check yourself. Okay, and if you have difficulty with this one, please let me know, and we're going to go step by step to see if it's correct or not. Once I find P, or is it 4? Oh man, 2 to the power 3, probably 8, probably 4. I'm not sure. Okay, you guys need to check this number in here. Okay. Yeah, it should be 8. It should be about 8.
The orbit is 8 years.
Yeah, that's but did you check it? Did you do the number?
Yeah, I did it right now.
Okay, very good. So the velocity then is equal to 2 pi times the radius, and the radius is a, divided by this number, which is 8 years. But this is in astronomical units. If a is equal to 4, it's in astronomical units. So it's 2 times 4 is 8 divided by 8. So it's pi, which is 3.14 astronomical units over per year. I need to make sure that these numbers are actually in proper units. Astronomical unit is 150 million kilometers. They want it in kilometers. They don't want it in astronomical units per second. So this is 1 AU is 150 million kilometers. That's easy. A year is 365 days, and a day is 24 hours, and an hour is 60 minutes, and a minute is 60 seconds. So now I plug in everything in the calculator, and I should find the speed, v, which is pi, 3.14, times 150 million, divided by 365 times 24 times 60 times 60. This is going to be in kilometers per second, okay? So this is in a nutshell all of the problems, actually. I didn't do them in detail. I'm hoping that you guys will do them in detail and learn something or two from the numbers. They're extremely important, okay? They're extremely valuable, so we really have to do that. And if you have difficulty or if you have no access to a good calculator or if you're not sure, please let me know so that we can do that. Work in teams, that's the ideal thing. I have 2 items of discussion today. And again, we have the entire work for the week, which is chapter 34, units 34 and 35, which hopefully you guys are going to do them. And there will be also quizzes down the road, and the exam is not too far. So we have an exam that we really need to focus on. And that's it. I have about 2 minutes and the other class need to start. So unless you guys have any questions, we're going to stop the recording, and I will see you guys next time. Okay? No questions? Good. So I'm going to stop the recording. Kevin, did you say something, or are you going to say something?
Oh, no, I have no questions. Thank you.
Okay, very good. Okay, so I'm going to